Hi, class. Today we are continuing our discussion of Chapter 5 in our Thermodynamics textbook. And for our first lecture for Chapter 5, we covered the idea of mass balance and how it applies to an open system. So today we're going to be talking about the first law of thermodynamics for an open system, and we're going to look specifically at two types of open systems. One is a steady flow process, and the other is a uniform process. Now, if you look, this is on behind me, this is our class Moodle page, and for your Moodle page, I've put some notes for Chapter 5, Video 2, Steady Flow and Uniform Flow. These are the notes that I'll be using for today's lecture. So I'll put them up on the screen, and I would like you to follow along with these as we talk. There we go. All right. So first of all, flow, work, and energy of a flowing fluid is what we're talking about today. And the first law of thermodynamics for an open system is the topic. And specifically, an open system is also called a control volume. The first law is always used in concert with the conservation of mass equation. Now, when we have a closed system and we don't have mass entering or exiting the system, the use of the first law of the use of the material balance or the mass balance equation becomes somewhat trivial. But when we have an open system where we have energy moving in and out through heat and work, and we also have energy moving in and out associated with mass, the material balance equation or the conservation of mass equation is not trivial, and we always have to use the two equations together to find a solution to our problem. So I'm going to start with two large cases of the first law of thermo, and then we eliminate terms in order to get down to a more specific case. So in general, if we have an open system, we have an energy in the system at time 1. We have some masses coming in, so that's subscripted M sub I. We have some masses exiting, subscripted M sub E. We have heat in and out and work in and out. And so we have the energy at time 1 plus the energy that comes in minus the energy that goes out is equal to the energy at time 2. Now, this energy can be associated with heat, work, or mass, as can be the energy in and out. So what we're going to do today is to break that down specifically as to what those terms look like. The first point I wanted to make is in our property tables, we have the quantity of enthalpy, and we've not really talked very much about enthalpy to this point. We've talked more about U, internal energy. Well, H is a state property, and its value is U plus P times V. So if we look at extensive enthalpy, capital H, it's equal to capital U plus P times volume. If we look at intensive enthalpy, we are talking about intensive internal energy plus P, pressure, same pressure, only this time times specific volume. So because H is the sum of state variables, H is itself a state variable. So when we talk about H, it turns out, this is just from an engineering point of view, there are some very good scientific reasons for this, but H is more often associated with a moving fluid, so the fluid's coming in and out of the control volume, whereas U is more associated with the stationary fluid or the mass in the system or control volume at time 1 and the mass in the control volume at time 2. So just to break it down, if we have mass flow rates, MI dot, those are the mass flow rates coming in, ME dot, the mass flow rates coming out, we'll generally see the energy term associated with those streams as being H for H in and H out, whereas the masses within the control volumes at time 1 and time 2, which are subscripted 1 and 2, are more commonly U values or internal energy values. So what is the difference between a steady flow process and a uniform process? Well, they're just special cases of any type of a process. But specifically, a steady flow process is a process in which the amount of mass in the system at time 1 is the same as the amount of mass in the system at time 2. Now, the actual mass itself and the energy state of the mass can be different. For example, if you have a pipe and you have fluid flowing through the pipe, the mass amount, if the pipe is flowing full, within a chunk of that pipe is always going to be the same, assuming that you have an incompressible fluid and so forth. But the actual mass that came in and passed through would be different. So, but if you have the same amount of mass in the system at time 1 as you do at time 2, the term dmc/dt, or the rate of change of mass within the control volume with respect to time, is equal to 0. And so the mass balance equation, or conservation mass equation, just tells us then that the mass flow rates in, if I take the summation of all the places where mass is coming in, I take those flow rates and add them together, those will be equal to the summation of the mass flow rates out. And so this is the mass balance, or the conservation of mass equation, and the energy balance, or the first law, which can be written as rates, Q dot, rate of heat transfer, minus W dot, which you can think of as rate of work or power, is equal to the summation on the inlets of M dot times H, which, as I said, you often see that with flowing mass. So here we have M times the quantity H plus V squared over 2, that's a kinetic energy term, plus GZ. So if you had 3 outlets, you would have 3 of these these terms. Now, on the outlet, you have the same types of terms where you have M dot times the individual enthalpies, kinetic energy, and potential energies. All right, so for a uniform flow process, it's a little bit different. This, instead of being like a pipe, might be like a bathtub, or it's a charging or discharging process. So, for example, if you're filling a bathtub with water, you have a mass of water in the tub at one time. You add some mass of water by the spigot. You drain some mass out from the drain, and you end up with the mass at time 2. So over this interval, we can write the mass that went in minus the mass that went out is equal to the change of mass in the system. And that's a statement of the mass balance equation, or the conservation of mass equation. Now, the interesting thing about this is that the energy does not have to be the same. In other words, what if you added hot water to a cold tub? So you had a little bit of mass in the tub, and you felt like it was too cold. So you added more water, only you added very high temperature water. What's going to happen is, even though the mass is the same, the energy state at the end of that process is going to be significantly different. So we can write the energy balance for uniform flow problems not as rate equations. So we're not talking about rate of heat transfer or rate of work or power, but we're talking about amount of heat and amount of work. And we can say that that's equal to the summation of MH on the outlet, MH on the inlet, plus M mass at time 2 times the internal energy, not enthalpy, but internal energy at time 2 in the control volume. In other words, in this instance, in the tub, minus M1 times U1. Okay, so we talked about the difference then between a closed system and an open system, where, and these are just little diagrams I had for a pipe with mass coming in and mass coming out, and a tub with mass coming in. And if the tub is very hot and it's in a cold room, you could have Q going out. In a bathtub, work is kind of squiffy. You'd have to put a stirrer or something in the tub. So maybe a jacuzzi would count for something like that. So anyway, at that point, we define flow work or flow energy as being the intensive enthalpy plus the intensive kinetic energy plus the intensive potential energy. And so the total or capital work or energy would be the mass times that amount. And if we're talking about the total rate of work or of flow work or energy, it would be M dot, or the first derivative of mass with respect to time, times theta, which is flow energy. All right, so at that point, what I'd like to do to demonstrate this is to work a problem. And if you begin in your textbook in chapter 5, section 2, you'll see that the authors divide up appliances into steady flow problems, the types of problems that lend themselves to steady flow analysis, and the types of problems that lend themselves to uniform flow analysis. And the first problem that I worked, 5.3 or 530, pardon me, is a nozzle, which a nozzle's purpose is to take fluid from a larger cross-sectional area. So fluid comes in here and exits here. The nozzle is smaller. The fluid speeds up. Heat can be lost. In this case, we're losing heat at a rate of 25 kilowatts. Typically, with a nozzle, there's no work done. The purpose of a nozzle is not to do work. The purpose of a nozzle is to speed up the fluid or to change the pressure from the inlet to the outlet. So we're told that this particular nozzle is being fed steam, which of course is a compressible fluid. The state of the steam going in is at 400 degrees centigrade and 800 kPa, and it's entering with a velocity of 10 meters per second. We're further told that the cross-sectional area of the inlet is 800 square centimeters. Coming out, we're told that the steam is at 300 degrees centigrade, 200 kPa. So you see the temperature has decreased, the pressure has decreased. We want to know what is the velocity on exit and what is the volumetric flow rate. Well, if we look at this one step at a time, we've had the tools to evaluate the volumetric flow rate for a while. Because if there's no mass accumulating or discharging from this nozzle, the nozzle just gets full and then it pushes mass from one side to the other. The mass flow rate in is going to equal the mass flow rate out. But because it's a compressible fluid, the volumetric flow rate on the exit and the volumetric flow rate on the entrance are not going to be the same. But we have enough data to compute the mass flow rate on the entrance, because we know that mass flow rate is rho AV, and that rho is 1 over specific volume, which we have in our tables. So we can say that mass flow rate is equal to A, the cross-sectional area, times the velocity of the fluid, divided by the specific volume of the fluid. Now we further know that the mass flow rate out is the same as the mass flow rate going in. And we also know that if we rewrite this equation, that mass flow rate is equal to volumetric flow rate over specific volume. And because we have the state of the exit defined, we can compute specific volume, and we can use that to find out what our volumetric flow rate would be, because volumetric flow rate would be the area times the velocity. All right, so that's actually, we can work that out right here. If we use the inlet data, we say that mass flow rate is equal to AV over V. A is given in square centimeters, so if you take square centimeters and convert it into square meters to have a consistent set of units, there's 100 centimeters per meter, and since it's squared, we have to do that conversion twice. So we take the number 800 and divide it by 100, divide it by 100 again to get square meters. So the cross-sectional area on the entrance, 800 square centimeters, is the same as 0.08 square meters. So we put that data here, times the velocity divided by the specific volume, which we get out of our property tables for steam at the entrance conditions. We find that our units cancel nicely, and we come up with a mass flow rate of 2.08 kilograms per second. Now we found that value from the data on the inlet, but the mass flow rate on the exit is exactly the same. The volumetric flow rate is not the same. So on the exit, how do we calculate the volumetric flow rate? Well, using that same equation, we take the mass flow rate on exit, which is the same as the mass flow rate on the entrance, multiply it by the specific volume, cancel units, and we get a volumetric flow rate of 2.74 cubic meters per second on the exit. Right, so now we know some stuff about the mass flow rate, the volumetric flow rate, and the last question they want to know is, what is the velocity of the fluid? Well, it stands to reason that the steam is going to speed up from here to here, but we can use the first law of thermodynamics to determine what that is. So we write down the first law for steady flow, and I cross out the terms that are not relevant or that are essentially zero, or that the deltas are essentially zero if we have a subtraction problem. So first of all, we have summation signs on the inlets and outlets. For a nozzle, we just have a single inlet and a single outlet. So we can get rid of those. We know that since we only have one inlet and one outlet, the mass flow rates are the same, so these values are the same. We do know what Q dot is. We're told that we lose heat at a rate of 25 kilowatts. And so we can rewrite this equation, say Q dot is equal to M dot. Oh, the last thing I forgot is that the GZ would be the potential energy term. We don't really have any difference in potential energy between the inlet and the outlet, or the exit. So we can eliminate those terms, not because they're equal to zero, but because the difference between them is equal to zero. So we can rewrite the equation as Q dot, just by eliminating terms, is equal to M dot times H enthalpy of the inlet times the velocity, the kinetic energy on the inlet, minus the enthalpy of the exit minus the kinetic energy on the exit. All right, so continuing with that thought process, what we want to solve for is the velocity on the exit. So we can bring this term over to the left-hand side of the equation, bring this term over to the right-hand side of the equation, multiply everything by 2, take the square root of the right-hand side, and we have an expression for the velocity of the exit. When we plug in our numbers, we see that we have, this is in kilojoules per kilogram, and kilowatts per kilogram per second. Now, meters squared per second squared as a unit, when we take the square root of that, is a good unit for velocity. But how does kilojoules per kilogram and this nonsense over here relate to meters squared per second squared? We can plug in the numbers and bring together like terms with like units, and we are left with these two that we have to figure out what the units look like. So proceeding to the next page, I take kilojoules per kilogram. A kilojoule is 1,000 or 10 to the third joules, which is a Newton per meter. So a kilojoule per kilogram can be written as 10 to the third Newton meter per kilogram. Force is equal to mass times acceleration. Newton's second law tells us that a Newton is equal to a kilogram meter per second squared. So here for Newton, I substitute in kilogram meter per second squared. I have another meter, so I multiply meter by meter to get meters squared. I have a kilogram on the bottom. So kilograms cancel out, and I'm left with meters per second squared. So what I find from that is a kilojoule per kilogram is 1,000 meters squared per second squared. Similarly, when I go through the work for a kilowatt second per kilogram, I find that a kilowatt second per kilogram is also equal to 1,000 meters squared per second squared. So using that conversion on my numbers, I can see that I come up with a value that's the value inside of the radical. The radicand has units of meters squared per second squared. So when I complete this operation, take the square root, I have an answer of velocity is 644 meters per second. So that means that the velocity, first of all, is in good units, and second of all, is quite a bit faster than it was on the inlet. All right, class, that's it for today. I have also posted your homework for the entire chapter 5 right here. Submit homework chapter 5, or submit homework number 5. And this is a complete list of problems for chapter 5. We have one more video for chapter 5, so you're not able to do all of these problems yet. But when I record the next video, there'll be a total of 3 videos for chapter 5. And when all 3 of them are up, you'll have the material you need to do your homework. Thanks very much for your attention.